Okay, so let's just recap where we were. Okay, so we laid out an outline for what we're going to do in the remaining classes. The first thing that we need to do is we need to understand intuitively what this stress energy tensor is. Okay, that is the thing that's sourcing the gravitational field, so we need to understand what it is. Then we'd like an argument for why this particular equation was Einstein's equation. I mean, after all, we just argued that some rank 2 tensor is equal to some other rank 2 tensor. But why this rank 2 tensor? Okay. So, for example, why do we use the Einstein tensor on the left? Why not, for example, the Ricci tensor? Okay. So we would like some more intuition for why this is the right equation as opposed to other possible equations that you could have written down. The other thing that we'd like is also to understand, for example, why this constant is not some other constant. Why is it 8 pi g Newton, right? Why is it not 10 pi g Newton or something completely different, right? So that's something else that we'd like to understand. And ultimately, whatever this constant is, it has to be related to the fact, since it's Newton's gravitational constant, in some limit from Einstein's equations in general relativity, you should be able to get Poisson's equation of Newtonian gravity. Okay, so what is that limit which gives us Newtonian gravity and the laws that we're familiar with, right? Because in the domain of validity, Newton's laws of gravity work extremely well, right? So if GR contradicts that, then there must be something wrong with GR, right? So we need to ensure that somehow this law, which has a completely different starting point, still gives us Newton's laws in some particular limit. Okay, so we'll see that this is true in what is called the weak field, that is when the gravitational field is not very strong, plus when the test particles and the source particles are slowly moving. In that limit, you get Poisson's equation and the motion of particles in that gravitational potential. Okay, but in addition to this, we'll also see that there are corrections to Newton's laws of gravity. Okay, and we'll see what some of those corrections are. Okay, so today what we're going to do is we'll focus on the first thing. Okay, we'll try to intuitively understand a little bit more about what the stress energy tensor is. And we will, maybe if we have some time, we'll start building up towards this argument of why this particular law is the correct law for gravitation, and how, and over at least if not this class, the next class, we'll try to show that in some particular limit you get Poisson's equation out of it. Okay, so let's start today with talking about the stress energy tensor. Okay, so this discussion is going to follow roughly Sean Carroll, okay, chapter 1 of Sean Carroll's book. Okay, so let's start with special relativity rather than general relativity. Okay, so the main idea is we wanted some kind of source for the gravitational field. Okay, so now in special relativity, in Newtonian mechanics, the source was rho, which was the mass density of a particle. Okay. Now in special relativity, what would be the generalization of this? Okay, in special relativity, for a single particle, you can characterize its energy by a single 4 vector, which is p mu. Okay, the single 4 vector has all the information about the energy and momentum of the particle. However, what p mu does not capture is the fact that the particle itself is moving. Okay, it moving from one place to another. So this momentum, this energy and momentum, is actually being transported as the particle is transported. Okay, and it's moving to a different point in space and time. So p mu does not capture the spatial location or the time variation of the flow of energy and momentum. It doesn't tell you where this energy and momentum is stored in space and time. Okay, so what you really want to do to specify where this flow is, okay, where the energy and momentum is stored at any point, is to look at the form momentum, okay, and also the trajectory of the particle. Okay, so this p is for the particle, okay, x mu is the coordinates of the particle, and maybe you parameterize it parametrically as some function of some parameter lambda. Okay, this could be proper time, it could be some other parameter. And basically you'd like to specify both these quantities. Okay, you specify both the energy and momentum and the position of the particle, okay, parametrically. And these together tell you, okay, as this particle is moving through space and time, how the energy and momentum of this particle itself is being carried along through space and time. Okay. And it could be that this particle is acted on by other forces. It could be interacting with other particles and so on. So its momentum could be changing as it moves. Okay. But if you know both the 4 vector for momentum and the 4 vector for its position, right, then you know everything about the energy momentum carried with this particle and how it flows. All right. So what we would like, okay, is rather than specifying these 2 different objects, the momentum and the position, what we'd like is a single object, okay, some kind of tensor, which captures this flow of energy and momentum. Okay. So roughly speaking, okay, the stress energy tensor is a measure of the flux of 4 momentum p mu. Okay, that is how much 4 momentum p mu is being transported across a surface of constant x nu. Okay, so I'll give some examples of what this means. Okay, so this is some kind of measure of momentum transport, okay, in a system, or how momentum is flowing through space and time. Okay, energy and momentum both. Now, you would expect that this is the right generalization of rho as a source for the gravitational field, because rho captures only mass density. Okay, but you would expect that because of the equivalence of mass and energy in a different reference frame, okay, a particle carries can carry energy. So if you want a relativistically invariant statement, the thing to talk about is really the energy flow or momentum flow together. Okay, and energy and momentum flow together should source the gravitational field. Okay, rather than just the mass density itself. So this tensor field also is locally defined. Okay, in this is again we're back to special relativity. So this tensor is locally defined. Okay, which means that at every point x, space-time point x on the manifold in space and time, you can define what the stress energy tensor is. Okay, so if there's a particle there, maybe it's carrying momentum with it. If there's no particle there, maybe there's no stress energy located at that point. Okay. So it can vary from one point in space-time to another point in space-time. And such a flux, okay, now here's the important point, that this flux can be defined not just for a single point particle, but it can also be defined for aggregates of point particles. That if you have many point particles together, okay, and you zoom out from these many point particles, where in some approximation they behave like a fluid. So you have many point particles kind of scattered around, and you look not at the energy momentum of any one of these particles, but the aggregate energy momentum of all of these particles together in this smooth approximation. Okay, and you basically one more assumption that we make is that such a fluid is assumed to be in local thermodynamic equilibrium. That is, the interactions between these particles put them in some kind of equilibrium. Okay, and this equilibrium is such that that locally you can define a thermodynamic equilibrium quantities. Okay, that is, you can define things like so here's the picture. Okay, so we look at fluid elements, okay, rather than individual particles, and these fluid elements are at particular locations in space and time. Okay, and this is an aggregate of many point particles. Okay, so we're in some kind of smooth approximation where you've coarse grained over this and you're treating it as a single point in space and time. And the fluid element is characterized by some thermodynamic properties. Okay, rather than just p mu or a momentum associated with one particle, now it's associated with just thermodynamic variables. Okay, which is the aggregate behavior is only characterized by some simple quantities like density, pressure, entropy, and so on. Okay, so you lose information about the microscopic behavior of the individual particles, and you just see this aggregate thermodynamic behavior for still a small enough size, okay, that that this part of the fluid maybe behaves differently from this part of the fluid. Okay, but locally, this part of the fluid is big enough that it contains many particles, okay, for which I can define a density, an entropy, a pressure, a temperature, and so on. Okay, so so we can, and also because it's a fluid, it can flow, which means that this element can move. Okay, it can have a velocity as well. It can have velocity, it can have an acceleration. So you can define a density located with a point in space and time, a pressure associated with a point in space and time, an entropy associated with a point in space and time, and a velocity associated with a point in space and time. Okay, so all of these are characterizing the properties of, at a particular x and t, we are characterizing the properties of a fluid element, okay, an element of this fluid, okay. If it has a velocity, it's going to flow, okay, it's going to move to a neighboring point. Okay, so now roughly what we can guess is that the components of this T mu nu, okay, will depend on these local thermodynamic quantities. Okay, thermodynamic quantities plus maybe this kind of bulk velocity, which is characterizing the flow. Yeah, go ahead. Yeah, thanks. That's right. So that's a very important point. Thanks for bringing that up. Okay, all of the thermodynamic quantities that I'm talking about are intensive quantities. Okay, not extensive quantities. Extensive quantities depend on system size. These are intensive. So density and pressure we already know are intensive quantities. Entropy should be entropy per unit volume, and then it's an intensive property. Right, thanks. Okay, so it's small s rather than capital S. Okay. Okay. Yeah. So it could define things like temperature and so on. Okay. Yeah. So indeed, even for if the size of this fluid element is arbitrarily small, the intensive properties are still defined. The extensive properties go to zero, right? As the system size becomes sufficiently small. Okay. So now what we can do is we can understand what these quantities are. So T00, let's go back to the definition of what this heuristic definition that we gave of T mu nu, as a measure of flux of 4 momentum P mu across a surface of constant X mu. Okay. So if we look at T00, it's the flux of P0. Okay. Sorry, not of 4 momentum, of the component of momentum P mu. Okay. It's the mu component of the momentum. Okay, of P mu across a surface of constant x nu. So in this particular case, if we're looking at T00, we're looking at the flux of P0, which is the energy, okay, across a constant time surface, that is x0, okay, across a constant x0 surface. Similarly, if we're looking at T0I, okay, then we're looking at, again, the flux of P0 across a constant spatial boundary, that is the boundary xi, okay, let's say xyz. Okay, so we're looking at how much energy is flowing across either in time or in space. Okay, so roughly one thing that you could guess is this energy flux across a constant time surface is just the energy density. Okay, because if there's no flow in the fluid, right, what you're measuring is just the local energy density from one instant to the next instant. Okay, that's the energy density stored at that location. Okay, so this is roughly, you would guess, if there's no flow, this is rho. Okay, where rho is not the mass density but the energy density. Okay, this is the energy density if V is equal to 0. Okay, that is no flow. Okay, and this is true provided, this statement is true locally. Okay, so this description of T00 is local. It's at some point xt in space-time. We're defining what the stress energy tensor is. Okay, if at that particular point in space-time, okay, there is no velocity, okay, of that fluid element, then T00 is a measure of the energy density stored at that point. Okay. Similarly, T0I is the energy flux across a constant spatial boundary, and Ti0 is the momentum flux across a constant time surface. Okay, so Ti0 is a measure of Pi across a surface of constant x0. So again, this is a measure of how much momentum flow you have. Okay, it's a measure of the momentum of the fluid. Okay, one thing that we can't directly argue from this, but it can be shown, is that the stress energy tensor is symmetric. Okay, so the stress energy tensor is symmetric. Maybe there's an argument that we could make based on this heuristic definition, but this statement is true. Okay, so T0I will be equal to Ti0, and so T0I will also be some kind of Ti0 is some kind of momentum density, and T0I will also therefore be a momentum density. Okay, it will be the same momentum density. Okay, now these other components of Tij, okay, if I is not equal to j, then this is the momentum flux in the I direction. So let's take I direction to be, let's say in the x direction, across a constant j surface. So let's say the j surface is some constant y. So imagine that this is a constant y surface, okay, constant y. And imagine that this is the x direction. Am I getting this right? Yeah, so this is x, this is y, okay, and this is z. So constant y, let's say I've taken y is equal to 0. So I've taken this surface which has y is equal to 0. And I'm measuring, okay, so this is a plane, okay, this is the y is equal to 0 surface. And what I'm doing is it's a measure of the momentum flux in the I direction. So that is in the x direction. I have a momentum px on this side of the boundary and a momentum px plus delta px on the other side of the boundary. Okay, so it's a measure of how much momentum is flowing across, how much px momentum is changing or flowing across this boundary of a constant y surface. Okay, so this is going to be a measure of something called shear, okay, or viscosity in a fluid. Okay, that is one layer of the fluid which is here on one side of the boundary and one layer on the other side. They are sliding past each other. Okay, so that's a measure of the shear or the viscosity of the fluid. Okay, if they have different momentum. And if I is equal to j, okay, then you're measuring, let's say if I is equal to j is x, okay, this is a constant x surface, and you're measuring the momentum in this direction and how much momentum flow is there in the same direction across this boundary. Okay, so this is going to be nothing but the pressure exerted by the fluid. Okay, so it will be measure the pressure of the fluid. Okay, so this thing that I said that you can't prove is that the stress energy tensor is symmetric, but we'll just assume that this is true. Okay, now the stress energy tensor, the definition that I've given you is a completely heuristic definition. Okay, I've just said intuitively I gave you some definition of what the stress energy tensor is. Okay, formally, if I want to compute the stress energy tensor from some kind of starting principle, what you need to do is actually specify a Lagrangian. Okay, the Lagrangian contains the full dynamics of both gravitation as well as particles moving in a gravitational field or sourcing a gravitational field. If you give me the Lagrangian, I can tell you what the stress energy tensor is. But this formal procedure we're not going to get into. Okay, so we will just work with this heuristic argument, okay, of what some intuitive notion of what the stress energy tensor is. It is a measure of the flux of momentum p mu across a surface of constant x nu. Okay, that's the heuristic definition that we're working with. Okay, but by the way, this can be defined not only for particles, okay, or collections of particles, but any kind of field. Okay, so you could have electromagnetic fields where the momentum flux of, or you're talking about the energy transport or energy density of the electromagnetic field, the momentum density, and so on. And similarly, you can define these various concepts, T00, T0I, Tij, okay, shear of the electromagnetic field. All of these things can be defined. Okay, we're not going to get into those definitions. We'll just stick with fluids for now. Okay, which are aggregates of many point particles. Okay, so we'll make some idealizations, okay, about the kind of fluids that we talk about. So we'll talk about what is a so-called perfect fluid, okay, and in the rest frame of such a fluid, okay, so that is if we're looking at a particular fluid element, we're assuming that the velocity of that fluid element is 0, okay. So we're in the rest frame of this fluid element, okay, at this point in space-time. Now, this particular fluid element, a couple of things should be true. It has no momentum, which means that T0I, which is equal to Ti0, both of these are 0. Okay. The second thing is we'll assume that a perfect fluid has no shear viscosity, which means that this Tij is equal to 0, I not equal to j. Okay. So it doesn't have any shear, layers don't slide past each other. Okay. And so what you have are the only non-zero elements of the stress energy tensor then are T00, okay, and Tii. Okay, these other components, so if I write it as a 4x4 matrix, this is a 1 cross 1, this is 3 cross 3. Okay, these components we're saying are 0. Okay, that is what's said here. And this Tij, okay, the off-diagonal entries are 0. So what we're saying now is that the stress energy tensor is purely diagonal. Okay, so the stress energy tensor is purely diagonal, and so you'll have T11, T22, T33. Sorry, I should use upper indices. Okay. And everything else is 0. This is an assumption for an ideal fluid. In general fluids, this doesn't have to be true. Okay. So now for this ideal fluid, T00 we already argued is the energy density. If you're in the rest frame of that fluid element, then you're measuring the energy flux across a constant time boundary. And since there's no velocity, the energy is not flowing anywhere. Okay. So T00 is just a measure of the energy density. TII is going to be a measure of the pressure, okay, as we discussed before. And in general, you can have the pressure in the x direction to be different from the pressure in the y direction, to be different from the pressure in the z direction. Again, we make this idealization for a perfect fluid, or what is called an ideal fluid, that these fluids are isotropic, which means that the pressure is in all directions is the same. Okay, so the pressure Pi is equal to P. Okay, so with these assumptions, if I'm at a point, a space-time point x, and if I'm looking at a fluid element which has V is equal to 0, okay, then the stress energy tensor takes this form. It's just diagonal, and it has diagonal entries rho, which is the energy density, and these three components are all identical. They are equal to the pressure. Okay, so this is for an ideal fluid. Ideal fluid element at rest. Okay, it's just rho times PPP. Sorry, rho PPP on the diagram. Okay. Okay. Any questions here? Okay. So now what we'll do is, so in the rest frame of this perfect fluid, okay, so if you're in the rest frame, then that particular fluid element has a velocity. Okay, but in special relativity, I should talk about the four velocities. So I'll talk about the velocity u mu rather than the velocity v, okay, which is the 3 velocity. And I'll talk about u mu of that fluid element. So at that particular x and t. Okay, so if it's at rest, or if we're in the rest frame of that particle, of that fluid element, then we know that u mu is just going to be 1, 0, 0, 0. Okay, that's what you have for a fluid element at rest. So now this same matrix that we had written here, okay, we can now write it in a more covariant way by using this matrix, this u mu, this 4 velocity vector. Okay, so you can write it as rho times u mu u nu. Okay, u mu u nu you can think of as a tensor product of u mu with u nu, and that tensor product is something like this. In matrix notation, it's this tensor product. Okay, and this tensor product is just going to give you 1 over here and zeros everywhere else. So you see rho times this will just give you rho in the T00 entry. Okay, if I look at the other entries, okay, so now I want P to appear in the other diagonal entries. So what I do is I take eta mu nu. Eta mu nu is -1, 1, 1, 1. Okay, and I add to this u mu u nu. Okay, but u mu u nu in the rest frame is this 1, 0, 0, 0. So if I add these together, the matrix that I get is 0, 1, 1, 1. Okay, so now this is rho in the 0, 0 position and P in the diagonal positions. Okay, P11, sorry, in the T11, T22, T33, I just get P. Okay, so this is a more covariant way of writing this, because now we can figure out what T mu nu is in any other reference frame, because in any other reference frame, this fluid element will not be at rest. Okay, so if I switch my reference frame, this u mu u nu are no longer 1, 0, 0, 0, but that's okay, because this equation should still be valid in any other reference frame. Okay, because u mu and u nu will transform, rho and p will not. Okay, sorry. Is that right? Yeah, that's right. So this rho and p do not transform, but the u mu and u nu will transform as I go to a different reference frame. Okay, even though the rho and p do not transform, okay, as I go to a different reference frame, what should happen? Yeah, okay. Let me just move ahead 1 second. Okay, so in a general inertial frame, okay, so you now expect this to be true. Okay, and so what we're going to do is we're going to write it as rho plus p, okay, where I've clubbed this term with this term, rho plus p times u mu u nu plus p times eta mu nu, okay, p times eta mu nu. So this is what I have for T mu nu, and this is valid in a general frame where u mu is not non-zero. Okay, so even if the fluid element is moving, I expect that this is still the stress energy tensor of that moving fluid element. Okay. Now it can also be that the fluid is inhomogeneous, which means that this rho, p, u mu, all of these can vary from one space-time point to another. Okay, that is, I can have a different energy density, pressure, and force velocity at one point, and I can have another density, pressure, and force velocity at a different point. Okay, so we were talking about one fluid element, but of course this is a function of x, and okay, and each of these are a function of x. Okay, each of those is a function of x. They can vary from one space-time point to another. Okay, and the last thing that you need is typically, because these fluids are in local thermodynamic equilibrium, if you knew, let's say, the equation of state of this fluid, then you have some additional handle of what this pressure is, and you can relate the pressure to its density. Okay, so so typically we assume that the equation of state is of the form P is equal to omega times rho. It's not always possible to do this, but for certain types of fluids, it's possible to do this. Okay, you can write P as some omega times rho, where omega is a constant, is a simple choice. Okay, for more complicated cases, okay, omega itself may depend on rho, okay, or P. So so now that we have this choice, okay, let's try to understand a couple of different choices for this omega and what they would physically imply about the fluid. Okay, so if we take omega is equal to 0, what we're saying is that the pressure is 0. There's no pressure. Such a fluid is called dust. Okay, so these are dust particles where the dust particles are non-interacting with each other. Okay, so they only have an energy density, and that energy density is basically not because of their interactions, but because of their collective motion. Okay, so each of these particles has some collective motion. So there's some net force velocity associated with this bunch of particles, and these are assumed to be non-interacting, okay, or cold matter. Okay, so we'll typically assume that their internal velocities, okay, so this u mu is the bulk velocity, that is the average flow. But what we're assuming is that internally these particles have small random velocities, so their temperatures are low, or equivalently their pressures are low. Pressures are low enough that we can neglect them. Okay, so we're saying that the pressure is 0. Okay, so this is what you get with W is equal to 0, and in the rest frame of such a fluid, the stress energy tensor would take this form. Okay, in the rest frame. For radiation, that is, if you have relativistic matter, so now if you have a bath of photons, okay, or things like neutrinos, where the neutrinos are moving, well, they're almost massless, but let's say they have very high energy, so they're moving near the speed of light. Okay, so you have a random bunch of photons, and you can ask, well, what is the equation of state for this? Okay, how is the pressure related to the density? Okay, so if you've taken solve this problem in thermodynamics, to get the equation of state, you need to know some kind of fundamental relation. Okay, and for photons, this fundamental relation is only a function of u and v, the internal energy, the energy of the photons and the volume. It doesn't depend on the number of these photons. Okay, and from this you can work out what the pressure is. Okay, I won't walk through the details, but yeah, okay, let me not walk through the details. But what you can do is, given this particular form of this fundamental relation, you can work out the relationship between P and rho. And it turns out that in that case, P is equal to 1/3 rho. Okay, where this rho is basically U by V. okay, and P is equal to, how does it go? ds is equal to du by t plus p by t dv. Okay, I might have got this sign right. Du is equal to tds minus pdv. Yeah, I think this is right. Okay, so p by t is equal to partial s partial v. Okay, um, and I think I don't remember exactly. I think this is of the form u to the 4/3 v to the minus 1/3, but I have to check this. Okay. Um, anyway, whatever you get, okay, the result is going to be that p is 1/3 rho. Okay, so this is for a gas of relativistic particles like photons. And finally, you can also have something called W is equal to -1, which we'll call vacuum energy. This is actually something that has negative pressure. Okay, so this is not something that we're familiar with at all. We've never seen anything like this. But you could imagine W is equal to -1, which means P is equal to minus rho. So if the energy density is positive, that means the pressure is negative. Okay, and the stress energy tensor now takes this form. Okay, and this is a bit strange, right? Now, so you're saying that this is something which has negative pressure. Okay, so positive pressure is something that tries to expand. Negative pressure is something that tries to collapse on itself. Okay, it's unstable. Okay, so negative pressure would be something that would be unstable. Okay, or naively you think it's unstable. Okay, so you can write this stress energy tensor that I've written over here. Okay, you can write it as the energy density, which I'm assuming is some kind of vacuum energy density. I'm calling it vacuum energy density. Okay, times eta mu nu. Okay, where eta mu nu is -1, 1, 1, 1. So I put an overall minus sign, and you get exactly this. Again, this is valid in the rest frame of the fluid. Okay. Okay. Now the important point about this stress energy tensor is that the stress energy tensor satisfies a conservation equation. Okay, and this conservation equation is what we call a local conservation equation. Okay, which is partial mu T mu nu is 0. Okay, this is the equation that the stress energy tensor satisfies. Okay, so this equation in particular, okay, is you can show that this can be understood as a local conservation of energy. That is, what it roughly tells you is something like partial partial 0 t 0 0 plus partial I t I 0 is equal to 0. Okay, so roughly speaking, this is very similar to the form partial t rho plus something like del dot j, okay, is 0, which is a conservation equation. Okay, so what it tells you is that locally, if I have some energy density, the only way this energy density can leave this region is if there's a current or some kind of flow of energy which takes it out of that region. Okay, so energy and momentum doesn't just disappear and reappear. Okay, it's locally conserved, which means that if locally the energy is decreasing, this is negative. The only way that can happen is if there's a divergence of this current, which means this region is sourcing a current. Okay, a current of energy density, which is making energy density flow out of that region. Okay, so so this is a statement of local energy conservation. Okay, similarly, you can argue that partial mu t mu I is a statement of local conservation of momentum of the fluid, because again this is t0 I plus partial j t j I is equal to 0. Okay, and here this we already said is interpreted as the momentum density. Okay, and this tji is now a measure of the flow of momentum density out of some particular region. Okay, so the fact that the stress energy tensor satisfies this, okay, is really just a restatement of the fact that energy is conserved in the fluid and momentum is conserved in a fluid. It's only transported from one place to another, but it's not created or destroyed, okay, in the fluid. Okay, so you can show that in the non-relativistic regime, where the fluid elements have speed much less than c. So if I'm in reference frames where all the fluid elements have low speeds compared to the speed of light, you can show, and I'm not going to show this, okay, but you can show that basically this equation, the conservation of the stress energy tensor, really just gives you the standard fluid equations. Okay, you may or may not have seen these equations before. Okay, but this equation is called the continuity equation. Okay, it's what I just described. Okay, it's basically that the flow of energy, okay, is sort of locally preserved, in the sense that any energy that's escaped or any energy decrease in some region of space must be compensated by a flow of that energy into some other region of space, okay, into some nearby region of space. And the second equation, okay, which you get from these momentum conservation equation, this is called Euler's equation. Okay, it's a measure of the rate of change of velocity of the fluid. Okay, and again, I'm working in the non-relativistic limit. In the non-relativistic limit, this equation gives you exactly these Euler equations. Okay, where this is some gradient of the pressure by rho. This is an equation that is well known in fluid mechanics for how the velocity of the fluid changes. Okay, as you flow from one location to another. Okay. Yeah, and as I mentioned earlier, the stress energy tensor can also be defined for electromagnetic fields, scalar fields, etc. Okay, but we won't go into this for now. We'll just stick with fluids, okay, and these kind of ideal fluids, and talk about the stress energy tensor for these ideal fluids. Okay, so now let's come to the stress energy tensor in general relativity. So in general relativity, we will take the stress energy tensor of a perfect fluid to be defined by the tensor equation, okay, of this form. So this T mu nu, so now we're talking about the components of a tensor in a curved space-time, okay? So this is not special relativity anymore. This is T mu nu, the components of T mu nu. So there is some 2-0 type tensor, okay, on a general curved manifold. And this tensor we now write as, so we assume that locally at every point on the manifold, which I'll denote as x or x mu, okay, these are the coordinates of that point, there is a 4 velocity, there's a smooth velocity field that I can assign to all points on the manifold. Okay, this is the velocity of the fluid. So there's a u which I can assign, which is a which is a vector. Okay, it's a type 1-0 tensor. Okay, which I can assign to every point on the manifold. Okay, and this gives me the 4 velocity. Okay, this generalized 4 velocity at any point on the manifold. And I can now write the stress energy tensor in components at every point in the manifold as some density plus pressure times u nu plus a pressure times, instead of eta mu nu now, I have a g mu nu, okay, where g mu nu is the metric, okay, the general metric on the manifold. So this is my guess for the generalization of T mu nu to general relativity, that is when I have curved manifolds, okay, curved spacetime. So here rho and p are scalar fields and u mu is a velocity which is a vector field. Okay, and so that means in particular that rho and p are defined at different points on the manifold, and similarly u mu is defined at different points on the manifold. Okay, just like we had in special relativity, except now these are defined on a curved manifold in general. Okay, and this satisfies the conservation equation, but the conservation equation, we can't use the regular derivative anymore, okay, because that derivative is ill-defined, okay, because you can't compare vectors in different tangent spaces. So you have to take this affine connection as the derivative. So we take del mu of T mu nu is 0. Okay, so this is the correct conservation law on an arbitrary curved manifold. Okay, so our T mu nu is defined like this, and T mu nu satisfies this equation on a general curved manifold. Okay, so this is going to be sort of our definition of what the stress energy tensor is. We're only going to focus on the stress energy tensor of ideal fluids, but you could have other sources of stress energy. Okay, our focus for the rest of this course will be only on the types of stress energy which are sourced by ideal fluids. Okay, but again, ideal fluids themselves are a rich class. Okay, and if I want to specify which ideal fluid I'm talking about, then I need to specify an equation of state. Okay, and I need to tell you what W is. Okay, then we've seen some simple cases. W is equal to 0 is dust, W is equal to 1/3 is radiation, and W is -1 is a vacuum energy. Okay. Okay. Any questions at this point? Yeah. You can't. Okay. Sorry. The question is, for those who are online, the question is, how do you visualize negative pressure? Yeah. So. Yeah, well, okay, so sort of it's so negative pressure, I think, is associated with an instability. Um, I'm not sure if I can show that rigorously. Um, okay, so formally from this equation, okay, if I have some kind of fundamental relation which tells me entropy in terms of U, N, and V, right? There's no rule which tells me that the pressure itself has to be positive. Okay, that's not one of the axioms um, of thermodynamics. Okay, however, I think what will happen is that, okay, I don't know how to show that this will result in an instability. Heuristically, the argument that I had given was basically, okay, so one way you measure pressure, if you think about, let's say, a monatomic gas or something like that, right? One way you measure pressure is you surround this by walls, okay? And you measure, let's say, the force per unit area, that is, as particles bombard the wall and they bounce back, right? They will exert a force on the wall, and that you measure the average force per unit area, that's the pressure, okay? That's what you get. You can't visualize this negative pressure microscopically in terms of particles bouncing off of something. Okay. Um, one way I guess you could visualize it is the particles are kind of yeah. So sorry. The other thing is this force is outwards. The net force is outwards. Negative pressure would be that the net force is inwards. Okay, so it's kind of like the particles are attracting the walls towards themselves. Okay, that's sort of a rough hand wavy way to think about it, negative pressure. Okay, now the other thing is, I mean, we sort of said, this is an upgraded version of partial mu t mu nu for a curved manifold, but uh, why is this going to be true? Okay, actually, what we want is we want this to be true, but how do we see that from Einstein's equations that this will be true? Now, actually, because we want this to be true, you see that Einstein's equations, okay, that is, you want some kind of local conservation of stress energy, okay. Einstein's equations actually guarantee, okay, that this equation, this del mu t mu nu, will be 0. The reason is, if you look at Einstein's equation, this now comes to the reason for why we put the Einstein tensor here, and not the Ricci tensor, R mu nu. Okay. The reason is because now if we take the derivative of both sides, okay, we take the affine connection acting on both sides. The affine connection acting on G gives you 0. Okay, this comes from the contracted Bianchi identity that we showed. Okay, and I reviewed this contracted Bianchi identity when we discussed the key mathematical ideas. Okay, this was one of the important ideas. So because the Einstein tensor satisfies this Bianchi identity, this derivative Bianchi identity, it's guaranteed now that if you assume that Einstein's equations are true, then you will automatically get this, okay, as an identity. It will be identically true that this is 0, because Einstein's equations plus the Bianchi identity together guarantees the right hand side will also have zero derivative. Okay. So this explains why you would not want to choose, for example, R mu nu or the Ricci tensor on this side, because then you would not automatically guarantee, and in fact it would not be true in general, that the stress energy tensor would be conserved. Okay, if Einstein's equation had an R mu nu on this side. Okay, so in fact Einstein, when he first tried to guess what these equations were, he tried first using R mu nu, okay, the Ricci tensor, and later he corrected it when he realized that the stress energy tensor has to be conserved. He found that this combination, by virtue of the Bianchi identity, is divergence-less, or it has zero derivative. Okay, and he used that tensor here, okay, which is the Einstein tensor. Okay, so that's why the left-hand side of this equation looks more confusing than just one curvature quantity like the Ricci tensor. It has this combination of curvature quantities. Okay. So this explains part of why Einstein's equation looks the way it does. Okay, it explains why on the left-hand side you have this particular tensor, which is the Einstein tensor, rather than any other tensor. Okay, this particular tensor is guaranteed to be divergence-less by the Bianchi identity, and therefore that guarantees that the stress-energy tensor is automatically conserved. Okay. Now, one other interesting thing about this Einstein equation. So we haven't shown why this constant should be 8 pi gn over c to the 4. That will come in a next class probably. Okay, but let me just say one more thing about this stress energy tensor now. See, the stress energy tensor, when I plugged it in general relativity, we said that it also depends on g mu nu. Okay, it depends on the metric. So we now have a source term, okay, on the right hand side of Einstein's equation, which also depends on the metric. Okay, this also depends on g mu nu. So it depends on rho and p and u, that is, it depends on the fluid properties, but it also depends on the metric. Okay, and the left hand side also depends on the metric, and you're trying to solve for the metric. Okay, so the source itself depends on what the metric is. Okay, the source itself depends on what the metric is. Of course, I can still specify rho, p, and u without specifying g mu nu. Okay, so I can still specify the properties of the fluid. Okay, that is, I can still specify rho, p, and u, but and then I can solve for the metric. But the metric now appears on both sides of this equation. Okay, it appears on the left-hand side and the right-hand side of this equation, and I have to solve for g mu nu from using both sides. Okay. So the source term, okay, so this is a really important point, is that the source term is not independent of the metric. Okay, it depends on the metric. So this is unlike Maxwell's equations, right? When you solve Maxwell's equations, you're solving something like this: partial mu f mu nu is j nu. So you have a source here, but the source doesn't depend on the electromagnetic field itself, right? The source is independent of the electromagnetic field. I just specify a density and a current, and I can find the electric and magnetic fields. Okay, but here. Now imagine that Maxwell's equations was not of this form, but was really something like this. Okay, this is still a valid tensor equation in special relativity. So it's j mu times f mu nu. Okay, so now the right-hand side depends on the electric and magnetic fields. Okay, so really what this is, okay, if you had an equation like this instead of Maxwell's equations, what this would mean is, when I solve the equations, okay, these equations, this introduces a non-linearity. Okay, this is called a non-linear source term. Why is it non-linear? Well, we define non-linearity by saying if we have a particular source J1, okay, and we solve Maxwell's equations and we get a solution F1. We solve Maxwell's equations with J2 and we get a solution F2. If I now take a source which is J1 plus J2, the solution should be F1 plus F2 if Maxwell's equations are linear. Okay. Clearly, if I now have some kind of f multiplying j, okay, these equations will no longer be linear. I can't superpose these solutions anymore. Okay, these equations are non-linear. I mean, roughly speaking, imagine that if I forgot about the tensor indices, imagine that I divide by f. There's some non-linear combination of f. Okay, so and it's made more complicated by the tensor indices. Okay, so this is a nonlinear source term. Okay, so it should be linear in J. Each term should be either linear in F or linear in J. That's what we need. Okay, for linearity. So linearity is defined by being each term in the equation should be linear in F and linear in J. So Maxwell's equation, fortunately, are linear, which means we can superpose the solutions. Einstein's equations are nonlinear. The left-hand side is nonlinear, but also the right-hand side is nonlinear. Okay, what that means is if I have two fluid elements, if I have rho 1 P1 U1 and rho 2 P2 U2, okay, even the right-hand side I can't superpose. Okay, the right-hand side itself is nonlinear. Okay, because the solution depends on what the metric is, and I have to solve for the metric given a rho P and a U. Okay, the T mu nu depends on what the metric is. Okay, so this source term in GR is also nonlinear. So general relativity is highly nonlinear, right? It's not just the left-hand side of the equation that's nonlinear. Even the right-hand side of the equation is nonlinear. Okay, in a combination of source plus the metric. Okay. Okay, I'll pause for more questions here. Okay, so now that we've fully appreciated how difficult it is to actually solve Einstein's equations, right, because of all the nonlinearity and so on, let's actually try to solve Einstein's equations. Okay, because I mean, there's no point saying that we have these equations, but they can't be solved. Right, we have to try to work out some solutions, and maybe some simple limits. If we take, we can solve Einstein's equations. Okay, so one solution and one class of solutions will be the flat metric. Okay, the flat metric will emerge in the absence of any source. Okay, as a solution to Einstein's equation. But besides just the flat metric, once you have an exact solution, as I told you in a previous class, right, you can also perturb around that solution to get approximate solutions to Einstein's equations. So having one exact solution, which is eta mu nu, this is an exact solution, will be useful because now we will be able to perturb this to get approximate solutions. Okay, where h mu nu is a small perturbation. Okay. So so this is what we'll do next. Okay, and this approximation is called linearized gravity. Okay. So this discussion is going to follow section 4.4 of Wald's book on general relativity. Okay, so we'll solve Einstein's equations. That is, we'll solve this equation. Okay, we'll solve it in the vacuum, in a vacuum where T mu nu is 0. Okay, that is, there is no fluid, there's no source of gravity. Okay, so we'll assume that the manifold is R4. Remember, the manifold has to be given to you. Okay, so we'll assume that the manifold is R4, and so we don't know what the metric is. We have to solve for the metric, and we will solve for the metric in a coordinate system where we put some coordinates t, x, y, z on this manifold. Okay. Now, an obvious solution to Einstein's equation, okay, is so we're solving this equation, right? We're just solving this equation. So this is a nonlinear function of the metric, okay, and we've seen its second derivatives in the metric, and it's nonlinear. Now, what we've seen is one obvious solution to this equation is g mu nu is equal to eta mu nu. That is, everywhere on the manifold, you get exactly the same metric, which is in components, it's minus 1, 1, 1, 1. Okay, this is an obvious solution. Why is this an obvious solution? Because if the metric is constant, that is, it's independent of space and time, then what you have is the Christoffel symbols are all 0 because the Christoffel symbols depend on derivatives of the metric. Now, the Riemann tensor is constructed using derivatives of Christoffel symbols and Christoffel symbols, but all the Christoffel symbols are 0, which means the Riemann tensor is 0. Okay. So another way of saying this is if the metric is eta mu nu, or the metric is this Minkowski metric, then Minkowski spacetime is flat in the sense that it has no curvature. Okay, so Minkowski spacetime is the analog of Euclidean space, if I just take 3D Euclidean space and I compute the curvature, okay, which I'll give you as an assignment to do, okay, well, for more complicated examples, okay, you'll find that the Riemann tensor is 0, okay. So similarly, in space-time, okay, this corresponds to what is called a flat metric. It has 0 curvature, okay, the Riemann tensor vanishes. By the way, if I wanted to solve Einstein's equations, I could have also got solutions with this, and I could have also had arbitrary number of minus signs and plus signs. Okay, what is it that guarantees that I have this as the solution? I mean, so we had actually postulated this. So when I had written down the postulates of GR, one of the postulates that I had written was that the metric has a signature with one minus sign and the others are plus signs. Okay, so I assume that the metric has this signature. Okay, that means that there is some basis in which I can always write it as the first component, or the 0, 0 component having a minus sign. So Einstein's equations don't tell you the signature of the metric. Okay, so you have to postulate that this is the signature of space-time, and then okay, you'll get this as the preferred metric. Okay. Okay, so since the Riemann tensor is 0, okay, therefore the Einstein tensor is 0 because the Einstein tensor is just constructed out of these curvature quantities which depend on the Riemann tensor. Also, because this is a second order differential equation, this G mu nu 0 is a second order differential equation in the metric. Assuming some boundary conditions, let's say as Tx goes to plus minus infinity, okay, this is the unique solution with some boundary conditions. Okay, so in the vacuum, if T mu nu is 0, you get the Minkowski metric. Okay, so Minkowski spacetime is actually a special solution of Einstein's equations in the absence of sources. Okay, in the absence of sources, and assuming that asymptotically at large xt, your solution approaches this Minkowski spacetime, then everywhere else in the middle, also the spacetime is going to be Minkowski. Okay, the metric is going to be Minkowski, which means that it has 0 curvature, or what we call flat spacetime. Okay, this is what we mean by flat spacetime. Flatness is defined by no curvature. No curvature is defined by the Riemann tensor is 0. Okay, at every point in spacetime. Okay, so now we have one exact solution. Okay, so we have an exact solution in the absence of sources. Okay, so now what we're going to do is, sorry, let's just come back to this example. Okay, so let's keep looking at our exact solution. So now with this exact solution, so of course we had said that you have to solve Einstein's equations. Okay, 8 pi g t mu nu. So I'm just dropping the constants, and also you have to solve the geodesic equation simultaneously. Okay, or the particle equation simultaneously. You have to solve both these equations. Okay, because any particle which is present in space-time will contribute to the stress energy tensor, and in principle will source a gravitational field. Okay, now if we are working in the assumption of no back reaction, okay, we're sort of in the assumption that these particles that are in the space-time have a small stress energy tensor. That is, they're not contributing significantly, or let's say their masses are very, very small, for example. Okay, so they're not contributing significantly to the stress energy tensor. I have very few particles and they have very small masses. Okay, in that approximation, T mu nu is approximately 0. Okay, and the solution to Einstein's equations is the flat spacetime, Minkowski spacetime. Now what we can do is we are ignoring back reaction. Okay, strictly speaking, the flat spacetime is only valid when it's completely empty. There's nothing in it. Okay, there's nothing that can cause curvature of spacetime, no source of energy. Okay, even if one particle would be sufficient to cause some kind of curvature of spacetime. Okay, but we'll work in the limit where we ignore back reaction and we just assume that T mu nu is 0. Okay, approximately 0. And now we've solved for the metric. We solve for the metric. The metric is eta mu nu. Okay, and now we plug it into this equation in the absence of external forces. So we assume that there is no force acting on the particle that is non-gravitational. Okay, so this F is only non-gravitational forces. this was a postulate, right, for what this law is, this law of how particles move. Okay, and we said that in the absence of forces, they will move along geodesics. That's easy to see because in the absence of forces, the equation that they satisfy is m times del u is 0, which is just the geodesic equation. Okay, so particles will satisfy the geodesic equation where u is the tangent vector to the curve that they move on. Okay, so what you'll find when you solve this, okay, is now we're solving this in a particular background metric with a particular background metric. We're solving this in the background metric where eta mu nu, where g mu nu is eta mu nu. Okay, so now in this background metric, we can write down u in some in the coordinate system that we're using. Okay, so g mu nu is eta mu nu in one coordinate system. We're saying there's at least one coordinate system in which g mu nu is eta mu nu. Okay, that's what we said when we solved the equations. Okay, it's not going to be true that g mu nu is eta mu nu in a different coordinate system, right? I can always switch to spherical coordinates, for example, right? And in spherical coordinates, if I switch to, instead of t x y z, in t x y z the metric looks like this. But if I switch to t r theta phi, right, then the metric is going to look like something like this: 1 r square sine square theta, right? As you worked out, right? So so what we're saying is there's at least one coordinate system in which the metric looks like this. That's what we mean when we're saying that we solved Einstein's equations. Okay, we solve them in a particular coordinate system. Okay. So now in the coordinate system, in this Cartesian coordinate system, that is this one, okay, we want to solve the geodesic equation. So we want to solve del u is equal to 0 in the Cartesian coordinate system. With g is now equal to eta, okay, the flat spacetime metric. So in this coordinate system, what happens to the Christoffel symbols? They're 0, right? So this equation, if we write down u is dx alpha d tau, okay, where tau is some parameter, okay, you've already worked out that that along the geodesic, okay, what we're getting is d by d tau of u alpha is 0, okay, because in general you'll have also this combination of Christoffels. Okay, but yes, the comment. Yeah, well, double derivative of x, not double derivative of u. Okay. Yeah. Okay. So the solution will be that u is a constant. Okay. Or really, what you will get is this will be the geodesic equation, right? In the when gamma is 0. Okay. Okay. This is basically d by d tau of u alpha is 0. Okay, because dx alpha d tau is the pore velocity. So what you get is u is a constant, and I mean I'm also using the fact that the parameter can be, the affine parameter can be taken to be the proper time. Okay, this is again something that you showed in the mid-sem exam. Okay, the affine parameter can be chosen to be the proper time, and also this u satisfies this property that ua is equal to -1. Okay, so we assume it's a time-like geodesic. Okay, again, the geodesic equation doesn't tell, this equation doesn't tell you that the particle moves on a time-like geodesic. This equation would tell you that any geodesic equation would, any geodesic would satisfy this equation. You have to impose this additionally. Okay, just like how we impose that the metric has signature with one minus sign, we also have to impose that particles only follow time-like curves. Okay, they only follow time-like curves. So in the absence of external forces, they follow time-like geodesics. Okay, if I have a general f over here, then the particle will not follow geodesic. Okay, the particle will not follow geodesic. F will cause deviation from geodesic behavior. but the particle will still follow a time-like curve, okay, which means the tangent vectors to whatever curve it's following will always be such that u inner product will be negative. Okay, so this is an additional imposition that we make, okay, on the solutions to this equation. Okay, and as you've seen on the midsem, okay, again, so if I solve this equation, I solve this equation for to find the trajectories of particles, what I'll get is the particle has constant velocity. It has constant forward velocity or it has constant velocity, where v is dx by dt. And the other condition is now that the speed has to be less than the speed of light. Okay, that's the other condition that's imposed by the fact that you're requiring that these geodesics be time-like. So the trajectories of inertial particles in flat Minkowski spacetime, that is, when the metric is this, if I have a test particle which is not sourcing any gravity but just moving in this gravitational field, which is basically no gravitational field, this test particle will just follow will have a motion with v is equal to constant, okay, and this magnitude of the speed is less than c. Okay, so we see that the equations that we're getting, okay, or the equations that we had sort of guessed, really give us the right behavior, at least for this particular solution. Okay. Okay, any questions at this point? All right, so now we'll do the next thing, okay, which is now we have one exact solution. Okay, this is very powerful. This doesn't seem like much, right? It seems like a very trivial solution. But really, you can get a lot just from knowing one exact solution. Okay, later we'll construct other exact solutions. But with this one exact solution, you can now perturb around this exact solution. And this solving Einstein's equations with this perturbation around vacuum, okay, is called linearized gravity. Okay, so let's look at this linearized gravity. And this linearized gravity is exactly kind of along the lines of what we were trying to guess when we were guessing Einstein's guessing the laws of gravity to begin with. Okay, of course, the full theory of general relativity has a lot of structure in it because of this additional single guess of this single principle, which is that the laws of physics have to be coordinate free. Okay, the laws of physics have to be coordinate free. That tells you automatically that the equations have to be non-linear. Okay, the equations that we got were completely non-linear equations. Okay, but we're working in an approximation. Okay, and this approximation is called linearized gravity. So what is this approximation? So if we look at this again, this Einstein's equation, we will basically assume that the stress energy tensor is somehow small. Okay, we'll assume that the stress energy tensor is small. Now, this is a bit complicated to do, okay, but basically we can assume that the rho and p are small. Okay, so if the rho is small and the p is small, then we'll assume that okay, one way to characterize their smallness is to say that, okay, they have a prefactor lambda in front of them and lambda is much, much smaller than 1. Okay, so the actual density is something like this. And the pressure is something like this. Okay, and you can think about this lambda as being some very, very small number. Okay, or that's what we mean when we say that the density rho prime is small. Okay, so what we're going to do is we're going to keep the lambda explicit. Okay, we're going to keep the lambda explicit, and at the end of the calculation we'll set lambda is equal to 1. But what we really mean by that is rho prime is somehow small. Okay, small compared to what? Well, we've not defined that very clearly yet. Okay, but let's just say that it's some kind of small quantity, and now we want to solve Einstein's equations, and we're keeping lambda explicit just so that we can keep track of which quantities are small. Okay, so so we'll replace T mu nu because T mu nu depends on rho p and combinations of rho and p. So we'll write it as lambda times T mu nu. Okay, lambda keeps track of the smallness of T mu nu. Okay, it keeps track of how small the components of T mu nu are. And at the end of the calculation, we're going to set lambda to 1. Okay, so we're going to write down this metric G mu nu is equal to 8 pi gn over c to the 4 lambda times T mu nu. Okay, now again, when you're solving for G mu nu, okay, we know that if in the limit lambda goes to 0, okay, we know an exact solution. we know that the solution is just eta mu nu. Okay, that's an exact solution to this equation. So now if we take lambda to be non-zero, okay, that is if you multiply the densities and pressures by lambda, then T mu nu was equal to rho plus P times u nu plus P times G mu nu. Okay, so what our guess is now that when we scale rho and the pressure by some amount lambda, when we set lambda to be non-zero but finite, okay, so this scales as lambda, this scales as lambda, okay, then the solution that we get, okay, will not be exactly this, okay, but it will have a correction, and these corrections will be can be expanded in a power series in lambda. Okay, so it will be lambda times some correction plus lambda square times some other correction. So this is the order 1 correction, there's an order 2 correction, and so on. Okay, this is a general expectation that order by order in lambda, okay, we can work out what this metric is. Okay, so we'll assume that there's some coordinate system in which when I solve this equation, okay, G mu nu is eta mu nu, but there are these order lambda corrections, okay, and I'll only work to first order in lambda. So till first order in lambda, G mu nu is in this coordinate system is eta mu nu plus some lambda times h mu nu of x. Okay, this is my assumption of what the solution looks like. Okay, and so the non-trivial thing now is to solve these Einstein's equations for what is this function h mu nu of x. Okay. All right. From now on, our convention will be that we will raise and lower indices using eta rather than g. Okay, so that is when I write something like h mu nu, what I mean by this is eta mu rho h rho nu. I do not mean g mu rho h rho nu. Okay, this is what we will mean by raising and lowering indices with eta. Okay, so this is just our convention. Okay, but you have to be careful because the things that appear, for example, in the Riemann curvature and so on, those are computed using upper G. Okay, so we have to be a little bit careful with this notation, okay, and not confusing it with the notation that we have used previously. Okay, so I'll try to explain where those differences come up. Okay. Okay, so of course, what I'm saying is that you need to differentiate these kind of raised and lowered indices which are raised and lowered using eta. You have to differentiate those from indices which are raised and lowered using the full metric G. Okay, so you have to be a little careful about this. The one exception to this raising and lowering is that when you write down the inverse metric, okay, this G mu nu upper, whenever we use this, we will use G mu nu upper to really mean the inverse metric computed to order lambda. Okay, so G mu nu upper will really be the inverse metric, okay, the full inverse metric. And this full inverse metric, so this has upper indices, but it doesn't obey this rule that I've written over here. Okay. So I've written G mu nu upper indices as eta mu nu minus lambda h upper mu nu. Okay, why is this true? Let's check. Okay, so this should be the inverse metric. So what this means is if I take eta mu nu minus lambda h mu nu, which I've just written here, and this G nu rho, which I've written as G eta nu rho plus lambda h nu rho, okay, and I expand this out. So I'll have eta mu nu times eta nu rho. I have minus lambda h mu nu times eta nu rho. Now by the rule that I had previously, okay, I'll use eta to lower the index. Okay, so which means that I'll lower this new index to a rho index like this. Okay, so here I'm using my rule for lowering and raising indices. And then I also have this cross term, okay, which is eta mu nu lambda h nu rho. And I'm going to use this to raise the new index to a mu index. So I'll have h mu rho. Okay. And I also have cross terms which involve lambda square, but I'm going to drop those. Okay, so I'll drop the order lambda square pieces. So now what I get is these two terms are exactly the same, so they cancel against each other. Eta mu nu and eta nu rho give me delta mu rho, okay, plus something which is order lambda square. So at least to order order lambda square, we can see that we've correctly computed the inverse metric. This is indeed the inverse metric. Okay. This is very similar to quantum mechanics, right? Where in quantum mechanics, you might have seen, if you've done a course on perturbation theory. Have you done perturbation theory in your quantum mechanics course so far? Probably not for the second year students yet. MSc students? Yeah, you've done it. Okay. So roughly speaking, the idea is like this. Supposing I have some exact matrix M, okay, and I want to compute a perturbation to this matrix. So it's some epsilon times this perturbation. Okay. Now I ask you, what is the inverse matrix? So let me call this matrix M prime. Okay. And I want to know what is the inverse matrix. Okay. The inverse matrix will approximately be M inverse minus epsilon P inverse. Okay. Where I'm assuming that the components of this perturbation are small compared to the components of the original matrix. Okay. Which I've made explicit by just putting an epsilon outside. Okay. So that's really what we've done here, okay, which is g mu nu is eta mu nu plus lambda h mu nu, okay, which we now written as g mu nu is eta mu nu minus lambda h mu nu, okay, with upper indices now, okay. So wherever we have an upper g mu nu in the definition of Riemann curvature, we will replace it by this quantity, okay, we will replace it by this quantity, eta mu nu minus lambda h mu nu. Okay. All right, now before we compute this Riemann curvature tensor, let me just say one more thing. Okay, so we assume that we are working in a coordinate system in which the solution to Einstein's equations takes this form. It's the exact solution plus this perturbation. Okay. Now we know that Einstein's equations, okay, because by their very nature are coordinate system invariant. Okay. Which means that we can always transform our coordinate system. Okay, so let's transform our coordinate system, and let's transform some coordinate system x to some coordinate system y. Okay, so in general, we can write our coordinates y as our coordinates x plus, I'll assume that this change of coordinates is a small change of coordinates, okay, not a large change of coordinates, which means that if I have a point x and I have some neighborhood of points around it, x gets transformed to something within its neighborhood, not something very far away from this neighborhood. So so the new coordinate y is x plus some small correction, which is lambda times some arbitrary function psi alpha of x. Okay, so these are arbitrary functions. Okay, but in some sense, I'm keeping track of the fact that these arbitrary functions are small. Okay, in my coordinate transformation by keeping this lambda over here. Okay, so I'm assuming I'm making a small transformation of coordinates. So what happens to the metric under this small transformation of coordinates? Well, we can use our tensor transformation rule to figure out how the components of a tensor transform. So if remember that this is a 0-2 tensor, okay, so we can use the rule for transformation of 0-2 tensor components. So we have g alpha beta x is equal to partial y mu partial x alpha, partial y mu partial x beta, g prime mu nu y. Okay, so this is the tensor in the y coordinate system, and this is now related to the tensor in the x coordinate system. Okay, by this transformation rule. This is just the tensor transformation rule. Okay, the general tensor transformation rule. And now what we can do is we can write, we can now differentiate this y with respect to x. Okay, so if we differentiate this, we get a delta mu alpha. If we differentiate this, we get a derivative of psi mu with respect to x alpha, which I'll write in shorthand as partial alpha. Okay, so this is an x derivative of psi. Okay, and similarly, this second piece over here gives me delta nu beta plus lambda times partial beta psi nu. Okay, whole thing times g prime mu nu. Okay, so again, you know, this is using the summation convention that I'm summing over mu indices because there's an upper mu and a lower mu, and an upper nu and a lower nu. Okay, which I'm summing over. Okay, so now let's expand this out. So if we expand this out, there's a product of these two deltas, delta mu alpha, delta nu beta. There is to order lambda, okay, these two terms contribute and the product of these two terms will contribute. So it's lambda times delta mu alpha times partial beta psi nu, and lambda times partial alpha psi nu times delta nu beta, sorry. This is partial alpha. Okay, plus order lambda square. Again, I'm going to drop the order lambda square pieces. Times again G prime union. Okay. Now, okay. So what we said was we started in a coordinate system X. Okay. In this coordinate system X, we assume that our metric took this form. That is, it was small corrections to H mu. Now, what we're demanding is that under this small coordinate transformation, okay, that the metric still continues in the new coordinate system, that is in the new y coordinate system, the metric still continues to be some small perturbation around eta mu. Okay, we're demanding that this should be true. Okay, so basically we should be able to write the metric in the new coordinate system as eta mu nu plus some lambda times h prime mu nu y. Okay, where h prime is a different function. Okay, a different set of functions compared to h mu nu. Okay, so this is the perturbation written in the y coordinate system. So now what we can do is we have a dictionary which relates the old metric to the new metric. We can now use this dictionary to relate the old metric perturbation, that is h, to the new metric perturbation, which is h prime. Okay. So what we'll do is we'll plug in for the metric on this side in terms of eta mu nu plus or eta alpha beta plus h alpha beta, and we'll plug in for the metric on this side as eta mu nu plus h prime mu nu. Okay, where this is a function of x and this is a function of y. Okay, so when we make that substitution, the left hand side is eta alpha beta plus lambda h alpha beta x. The right hand side is all that stuff that I'd written before times this metric eta mu nu plus lambda h prime mu nu of y. Okay, so now we'll compare terms of order lambda. Okay, so we'll compare the terms of order lambda. Okay, the order lambda to the 0 piece is exactly the same. This is eta alpha beta, and this times this is also going to give you eta alpha beta. Okay, because this delta mu alpha will convert this mu index to an alpha index. Delta nu beta will convert the nu index to a beta index. Okay, when I sum over nu. So now I only have to compare the order lambda pieces. So if I compare the order lambda pieces, what I get is on the left hand side I have h alpha beta. On the right hand side I have h mu nu prime. Okay, and I also have this times eta mu nu. This is going to be order lambda. Okay, but this involves derivatives with respect to x, so I'm going to move this over to the left hand side. Okay, so the left hand side of that equation is this. It's h alpha beta x minus eta mu nu times all of this. Okay, and eta mu nu times all of this is going to give me, okay, since I have a delta mu alpha, what I'm going to get is, yeah, okay. So firstly, this delta mu alpha will convert this eta to an alpha, this eta mu nu to eta alpha nu. Eta alpha nu times psi nu. Okay, I can write this. And by a definition of what is a lowering or raising of this psi index, we're now going to raise and lower by eta. So this becomes partial beta psi alpha. Okay, so that's this term. And similarly, the other term will give you partial alpha xi beta. Okay, and now I still have this thing, which is h prime alpha beta y. Okay, so at the end, what I've done is I've related the new perturbation to the metric in the new coordinate system. In the y coordinate system, the perturbation to the metric is this. In the x coordinate system, the perturbation to the metric is this. Okay, so the point is that the coordinate freedom that you had, okay, you had the freedom to choose your coordinate system. Okay, and the coordinate freedom that you have doesn't uniquely specify what the perturbation is, because I'm allowed to change coordinate systems. If I change coordinate systems, then my perturbation, instead of being h alpha beta, will become this new h prime alpha beta. But there's still a dictionary that relates them. This dictionary is just the perturbative version of the full dictionary, which relates arbitrary metrics under arbitrary coordinate transformations. Okay. So at linear order, the coordinate choice freedom leads to many equivalent perturbations to the metric. All of these are really the same description of exactly the same perturbation, just described in a different coordinate system. Okay, so there are many different choices of how you want to write that perturbation. All those choices depend on what I choose these functions xi to be. Okay, for any choice of xi is a choice of change of coordinate system from coordinate system x to coordinate system y. Okay, which is this choice. Okay, so for every possible coordinate system change that I can make, I will get a different form of the perturbation, but really these are the same physical perturbation. Okay, so these are equivalent perturbations. Now this freedom, right, to choose your coordinates in linear order, this is called gauge freedom. Okay, this is gauge freedom is a very important idea in physics. This is one manifestation of gauge freedom which shows up in general relativity. Okay, electromagnetic interactions have another type of gauge freedom. We'll see what the relationship is between the two. Not relationship, but similarities between the two. Okay, so under a general, if we had made a general coordinate transformation, that is the full symmetry of general relativity. But if we made a large coordinate transformation, then the components of H can become large, because in one coordinate system, if I have this, okay, under an arbitrary transformation, this metric will now become some G prime mu nu, and now it's possible that these corrections to eta mu nu may become large in some other coordinate system. Okay, so we had assumed that our coordinate transformation was such that our coordinate transformation itself was sort of a small coordinate transformation. Okay, so in general relativity, you are allowed to make large coordinate transformations. There's no rule against it. Okay, we are restricting to this particular class of transformations so that our perturbations are always linear. Okay, so we're restricting to this class of coordinate transformations. Okay. Yeah, all right. I think this is a good point to stop. So we'll stop here. Okay. So we will now continue from this point where we have basically perturbed the metric. But remember that there are many different coordinate systems in which you can describe this perturbation. Okay. And the dictionary that relates those different coordinate systems is given, takes the perturbation in one coordinate system to a perturbation in another coordinate system like this. For every choice of xi, I get one dictionary, okay, which relates me from one coordinate system to another. So now what we're going to do is in the next class, what we're going to do is we're going to plug this, or we're going to solve Einstein's equations in the linearized limit. That is, we will solve Einstein's equations. We will plug in for G mu nu in terms of this perturbed metric, okay, and we will try to solve Einstein's equations. Okay, so these will give us approximate solutions. These are not going to be exact solutions, but these approximate solutions will teach us something interesting. In particular, they will teach us that in one limit, Einstein's equations, in the limit of what are called weak fields, weak gravitational fields, you will actually get Newton's laws out of Einstein's equations. Okay, so that's what we're going to try to show in the next class. Okay, we'll stop here, and yeah, any questions? Yeah. So, sorry, can you be a bit louder, please? Yeah, we'll clarify that more precisely in the next class. Okay, it's going to be related to the stress energy tensor that you assume. Okay, because our starting point was to assume the stress energy tensor, the densities and pressures were small. But again, small in a particular coordinate system. Okay, if no more questions, let's just stop here. Thanks.